Hello everyone, welcome back. Oh, it seems like only half of the class is here. Where are the rest? Where are your friends? Can every one of you try to answer these questions? Those questions are posted by me actually. Because I have been receiving these questions for the past several days. So, can you try to answer these questions? What is the difference between hyperparameter tuning and grid search? And is it okay if hyperparameter tuned model results in lower accuracy? Can you think about this? Yes. So if you need an answer, can you please ask a question towards the end of the class, and we shall address these two questions again. Okay? But before we come to that, please think about it. Okay? So let's get started with today's lecture. It is a little bit lengthy today. I have about 50 slides. So as for today, we will be talking about artificial neural network, ANN. So this ANN is actually, the reason why we need to learn about this ANN is because those are one of the most simplest neural network architecture before we venture into deep learning, especially in computer vision and also natural language processing tasks. So as for this ANN, we know that it is powerful, but for the task that we have chosen for our assignments are most of the time not so suitable to employ this ANN in our very small data sets. So please, for this lecture, treat it as a learning, and we shall prepare ourselves with all of this knowledge as we venture into deep learning related knowledge. Okay? So for today, we will be going through some of the basic principles that we need to know when it comes to artificial neural network. We'll first introduce you to ANN, then the basic unit of artificial neural network, which is perceptron, the basic architectures that we usually see when it comes to neural network, backpropagation, activation functions, loss functions, as well as gradient descent, a question that some of your friends have raised last week. So last week, somebody raised a question about what is gradient descent, and today we'll be talking about it because it is very relevant when it comes to training a neural network. Okay? So let's first start with introducing what is artificial neural network. So artificial neural network is a type of machine learning algorithm which is inspired by the structure and function of how human brain works, the biological neuron. So how does this biological neuron work is that it will usually have the receiver that receives signals from any stimuli. And then it will pass on this signal to the next neuron through the axon terminals. So it receives some stimuli, say for example, a touch on your skin, and pass on this touch towards the next neuron. So with this passing on mechanism, the signal will finally arrive at our brain, and our brain will perceive whether somebody has touched us or have something touch on our skin, which is why sometimes when our stimuli is too soft, like say for example the aircon wind, we don't feel it on our skin because this neuron has a specific function that filters off this signal within a certain threshold. And this mechanism is also exactly applicable when we talk about neural network, how each neuron works from one neuron to another neuron. So ANN is a type of machine learning algorithm that can be used to solve a wide range of problems because it mimics the structure and function of our human brain. So we can use it for classification as well as regression task. So an introduction into this artificial neural network before we go to talk about the basic unit that represents this biological neuron. So first off, let's just take a step back and see what is this artificial neural network. I think this piece of information is something which is easier to digest and ingest and digest because this is something that we have already know before coming to this class. So neuron is usually organized into layers. We usually have an input layer that is responsible for receiving the input. So then we also have the output layer, which gives us the prediction. Okay? And in between this input layer and output layer, there are a lot of hidden layers. So this hidden layer, they are the neurons that are responsible for learning the complex pattern within our data. So these are hidden layers. Okay. So there can be one or more hidden layers. In the case where we have probably 3 to 5 layers, that is considerably a shallow neural network. And say for example, if we have beyond 10 to 20 layers, we can consider that as a deeper neural network that can be considered as deep neural network. Okay, so this is just a basic concept, and we'll come to what types of neural network architecture do we have, and we can stack them over and over again. Stack them one on top of each other. So that is a quick introduction into neural network. So now this neural network is composed of multiple neurons, and we can see that these neurons, every single unit here refers to this basic unit that has a receiver and something that gives us the output. And every of these neurons, they are interconnected. So the basic unit of these neurons in the terminology of artificial neural network is called the perceptron. So now we want to talk about what is perceptron. This will involve a little bit of mathematics, but we will keep it at very high level. So perceptron is the most basic or fundamental unit of this neural network. The function of this perceptron is, it is supposed to have a head that takes in multiple inputs. They are usually in a numerical format. So everything has to be encoded if they are not in numerical format. So then each of these input will then have a corresponding weight that signifies the importance of every single feature here towards our output. So then we have our x, which is what we see, and we have our weights. So taken together, we are taking the sum. We are taking this as the weighted inputs. So all of these weighted inputs will be summed together and pass on to a activation function before producing the output. And before we subject this summation function to provide our output, a bias term is also included. Okay, so a bias term is also added, and the function of this bias term is to shift the activation function horizontally. And what is this activation function? Activation function is a mathematical function which allows this neural network to include or to add this non-linearity concept into our model so that it can capture complex data patterns. So now, what we just talked about is a fundamental concept of how this perceptron would work. And if we were to write this, put this into a mathematical notation, it will be something like this. So the input, our input x, will normally be represented as x1, x2 to xm. Okay, so they will usually be represented as in a vector from x1 to xm. And every single inputs over here will be weighted, and these weights are exactly what our neural network is trying to learn from our data. Okay, so these weights, you can think of this as a coefficient that is similar to our multiple linear regression. Okay, so they are usually represented from w1 to wm. So we have compatible set of x and w, and therefore we will take the product of x and w, sum that up for our predictive task. And before we come to subjecting this summation function through an activation function to produce our output, we will also add on a bias term that can be thought of as w0, one of the weights that does not change, that is constant. Okay, so our output will then be calculated as this function. We are taking the dot product, the element-wise multiplication product, and the summation between our features and the weights. Then we add on this to our bias term. So this taken all together, the results of this summation and the addition to this bias term will be passed through an activation function, which is represented by G over here, to produce our predicted output Y of one single neuron. So this is how it works for one single neuron, which is one little circle which you see from the previous architecture. Okay, so now let's talk about what is this weights. So this weights is one of the parameter that we are trying to learn during the training process of a artificial neural network. So weights is the parameter. So those who have already done CV NLP, oftentimes we talk about these weights in transfer learning. We are transferring the weights. And so now you know exactly what these weights are. So these weights are a coefficient that represent how important a particular feature is within the data structure in its correlation to our output. So these weights are the coefficient that is multiplied by the input to each neuron. So these weights will determine how each input contribute to the output of our neuron. And the number of parameters here refers to how many weights do we have in our architecture. Okay. So now let's see how to calculate the total number of parameters which a neuron can carry, okay, which a network can carry. So say for example, we will have a very simple neural network over here. So this network over here, it has only 6 neurons. So even though there are more than 6 circles here, reason being, this tree at the input layer is not considered as a neuron. It's not considered as a perceptron. So from this hidden layer, from the first hidden layer onwards, every single little circle will be considered as one perceptron. Okay? If you still remember, the criteria for a thing to be classified as a perceptron is that it needs to have an input and the output. And at the first layer over here, these are the input itself. So it doesn't have any input that is channeled towards it. And therefore, this is not considered as a neuron or not considered as a perceptron. Okay? So now here altogether, we have 6 neurons. So how do we calculate the total number of parameters which a network is trying to learn? Because for multiple linear regression, it is very simple for us to calculate the parameters that we are trying to learn, right? The total number of parameters which a multiple linear regression tries to learn is referring to the weights of the total feature that we have plus the y-intercept plus 1, correct? So now, how do we know how much weight is our neural network trying to learn? So this is the calculation. So basically, every single connection over here, we know that this perceptron, they are interconnected from one another. So basically, every single line here will refer to one parameter which this neuron is trying to learn. So from here, if we were to have 4 plus 2 neurons, the total weights that we are trying to learn here will be altogether 20 weights. So 3 by 4, 4 by 2, because we know that every single neuron is interconnected to one another. Okay, so altogether here we have 20 weights. So now, because we have 6 neurons, every of the neurons will have one additional bias term, right? And therefore, in order to tabulate the total parameters that this neural network is trying to learn, is that we want to take the total number of connection that we are trying to learn plus the number of biases. Therefore, this little architecture here will have to learn a total of 26 parameters, 26 learnable parameters. Okay? So when it comes to deep learning, these numbers will add up to over 1 million parameters, which is why it is taking time to learn and to train and to predict sometimes. Yeah? This is the underlying logic behind the total number of parameters which we are trying to learn using this parameter. So at this point of time, what we just discussed is that neural network is a type of machine learning algorithm that is inspired by biological neurons. So a neural network will usually have multiple neurons that are stacked from one layer to another. And every single neuron in each of the layers are interconnected. Okay? So, and the knowledge about this learning task, they are represented as weights. They are usually refers to weights. Okay? So this is so far what have we covered. Any question? Okay, so if there's no question, let's see if we are able to calculate how many parameters are there in this bigger neuron. 9? How is that possible? 41. 12. In order to calculate the number of parameters, we will have to take 3 by 4, 4 by 4, 4 by 1, and plus 4 plus 4 plus 1. Okay, see if you get it right. So in order to calculate the total number of neurons in this neural network, so this network has 4 plus 4 plus 1. There are altogether 9 neurons. So 3 of these in red, they are not considered as one perceptron or one neuron because they don't have an input. They are the input themselves. Okay. In order to calculate the weights, we will take 3 by 4, 4 by 4, 4 by 1. Together, we have 32 weights plus 9 biases, and therefore there are altogether 41 learnable parameters. Okay. So then the next thing that we want to cover will be what types of architecture that we usually see as a perceptron. So the architecture of a neural network is usually linked with the learning algorithm that we use to train these neurons itself. So there are many types of neural network. The simplest type is single layer feed-forward neural network. We also have multiple layer feed-forward neural network, recurrent neural network, convolution neural network, and generative adversarial neural network. So of course, all of these networks are, this is not the exhaustive list. There are more types of neural network and there are more to come. And therefore, these are some of the important ones which we want to introduce in this module. So let's first start with single layer feed-forward neural network. So this single layer feed-forward neural network is a type of the simplest type of neural network. It is not so commonly used nowadays because it doesn't have any feedback connection between the neurons, which makes it limited to only learning the linear relationship. It is not able to capture any complex relationship. But this was one of the earliest type of neural network which was available when people create a neural network. So then, multi-layer feed-forward neural network is one of the most frequently used ones nowadays. So these neurons, they are usually organized into multiple layers. Basically, all of the neural networks are organized in multiple layers. So what is different between this multi-layer feed-forward neural network with the single-layer one is that it has feedback connections between the neurons in adjacent layers. So right now, instead of having just feed-forward neural network, we also have a mechanism which backpropagates that allows this neural network to be trained further, to adjust its weights to suit to our outcome. So we'll be talking about this feed-forward propagation and back propagation in a bit. So another type of most commonly used recurrent neural network is the recurrent neural network. So this recurrent neural network has feedback connections to themselves, which allow them to learn sequential pattern. So this type of neural network is usually used when we have to capture time series related data or natural language processing data, because we know that text or words, a sentence is just a sequence of words, and therefore this recurrent neural network is very suitable for natural language processing tasks. And for those who are interested in venturing into forecasting, this neural network, recurrent neural network, is also one of the very relevant recurrent neural network, as it is able to capture what happens historically before arriving at a particular row of data. So this is recurrent neural network. And the next type of, another type of neural network is the convolutional neural network. So this convolutional neural network, they are usually arranged, the neurons are arranged in the convolutional layers themselves. So this type of neural network uses filter to detect specific features. and they are widely used in computer vision tasks, especially for image classification, detection, as well as segmentation. And one of the function of this convolution neural network is its ability to capture spatial data. So previously, when we mentioned recurrent neural network, what it captures is sequential data which comes in sequence. But this convolution neural network is different from recurrent neural network in the way that it captures spatial data. So what it means here is it retains the structure of things within its dimensional space. Therefore, it is the best for us to capture what is in an image, which is usually represented in a 2D array. Okay, that is convolution neural network. And the third one that we want to cover here is GAN. So this is generative, sorry about the error. So this is generative adversarial network. So this GAN it consists of two competing neural network. It has one generator and it has one discriminator. So with the combination of the discriminator and the generator, this is the perfect type of neural network that allows what we see today, that is our chatbots. Okay, so the generator will first learn to create new data that resembles our real data. So then a discriminator will then be able to distinguish between the real and the fake, and therefore it is able to produce another set of output that mimics but different from the original data. Okay, so which is why this kind of GAN's neural network, generative adversarial network, they are usually used for generating images or songs. Okay, songs. Yeah. So what we just discussed here are examples of neural network architecture that is used for different types of tasks that we usually see. So the choice of the architecture will depend on the nature of data which we see, like for example, whether our features are independent of each other. So in those cases, those feed-forward neural network will be suitable. And then when our data consists of sequential information, then RNN will be suitable. And if we have to capture or retain a certain spatial information, that is when a CNN will become very relevant. Okay, question? Okay, no further question. What we want to talk about next is backpropagation. So backpropagation is ultimately one of the breakthrough within the machine learning field, especially in the community of neural network. This backpropagation allows this neural network to be modified into what it has become today. So before we talk about this backpropagation, we will have to understand how this forward propagation works. So how does this forward propagation work is that what we have here is we have the input and we have our hidden layers. So now what happens within this neuron is that every time we initialize the training of this neural network, we are initializing the weights at random values. Say for example, we see that every single line which we see consists of one weight. So at the first step, or the first time our network sees our data, it will just randomly assign some values to every single W. Okay, so it is going to produce a lot of errors at towards the end as the first time of output. Okay, so now with this initialized random weights, it is able to pass through the net to produce a certain output. So now backpropagation, it's a mechanism which can be summarized as follows. So now what it does here is it will begin. So now we have the first round of prediction versus our actual output. So what we are trying to do here, backpropagation on the first step, is to compute the error term for the output unit using the observed error. So the first time our neural network sees our data, it is randomly initializing the weights to produce a set of output which has high error. And the first step of this backpropagation is to compute the error term. So now from this error term that it computes, what happens here is from the output layer, it repeats the propagating error back to the previous layer and tell the previous layer that, hey, this is an error that you are making. Can you adjust your weights? Okay. So it is updating its weights or layers through the error terms one layer by one layer. Therefore, it allows this network to train to suit to our correct output. So this is how it works. So initially we have a set of input with randomly initialized weights. So with these randomly initialized weights, our network will produce a set of output. So this output will then be compared against with the expected output. So with these two in hand, we are able to tabulate the error term, which is in red. So now what happens in this backpropagation learning is that the error term will then be fed back to its previous layers. And this previous layer will go about and update its weights so that the next output will be very similar, or we want to offset the error that it sees for the first time from one layer to another layer. So this is the mechanism of backpropagation. So this backpropagation will be passed through every single hidden unit for one cycle. So one cycle is usually referred to one epoch. And as this process repeats, we are able to readjust the weights based on the error that it produced for every single circle or every single round. This is how a neural network is being trained to produce highly accurate output. Okay, so that is backpropagation. So how this backpropagation works in summary is that our input data will be fed to this neural network where a certain set of prediction is calculated based on randomly initialized weights. So then the error of the prediction will then be calculated and propagate back through the network layer by layer for it to adjust the weights over and over again until it reaches a certain point that the output is very close to our expected output. Okay, that is backpropagation, and that is the idea of how a neural network learns from our data. Okay, if there is no question, then let's proceed to another concept that we need to learn for this artificial neural network, that is activation functions. So what is this activation function again? So this activation function is something that allows this neural network to be able to learn complex non-linear pattern from our data set. So now, what is complexity? So we want to discuss a concept that is between the number of neurons that we have and the level of complexity that it is being able to capture. So one concept that we want to know, that we want to have, is that the more hidden neurons that we have in a neural network, the more complex pattern it can learn. So, and what is giving these neurons the ability to learn this complex pattern is the activation function. So this is one of the example. If we only have 3 hidden neurons, we can see that this network is able to learn a certain simple boundary. We can see that with this boundary, even though it is non-linear, but it is still having a lot of errors at the green side, as in we see some red color dots in the green side of the classes. So if you were to increase the number of our hidden neurons, this network is then able to capture a more complex decision boundary, where now it is able to classify further red dots from the green color side of the area. Okay, and as we increase more and more number of neurons, this neural network can then capture almost every single red dot at the initial green side of the clusters. So now there is also a tendency for this neural network to overfit. So now we want to talk about this activation function. So activation function is just some mathematical functions that is applied to the output of the neuron in a neural network. So this activation function will then decide whether a neuron should be activated or not by calculating the weighted sum and further add bias to it. And the purpose of this is to introduce non-linearity. So now what does it mean here? So for every single pattern that it is for every neuron sees, it will go and decide whether this neuron should be activated or not. If a neuron is activated, the message will then be passed through to the next neuron. If this neuron decides, this activation function decides that the neuron should not be activated, then the information will then just stop at a particular neuron itself and it will not propagate through. And that will be the output. So some of the famous activation functions are step function, sine function, sigmoid function, and also linear function. So this step and sine function, they are simple activation function that outputs 1 or 0. Okay? So if let's say 1, this neuron will be activated where it will pass through the information to the next neuron. If it results in a number of 0, then it wouldn't produce an output to the next neuron. Okay, so sigmoid function for backpropagation network outputs also values between 0 and 1. And this sigmoid function is one of the most widely used function for a binary classification task. A linear function activation functions will produce a series of values that is usually used at the final layer of our neural network, which is meant for regression task. Okay, so alongside with this step function, sine function, and sigmoid function, there are also some of the newer activation function which is pretty popular because they are known to be better compared to the sigmoid and step functions. So one of them is the rectified linear unit, the ReLU function. They are known to have improved performance and to improve the efficiency of the neural network. Okay, so this is how it looks like, and it is famous because of its gradient propagation properties, where it is able to produce very sparse representation. Okay, even though we have a very sparse representation, is a concept that will come true when we looked at bigger tasks like computer vision or natural language processing tasks. Okay, and these sigmoid and softmax functions are two of the functions that we usually use at the final layer of a particular neural network for classification tasks. So the difference between softmax at our level, the difference between softmax and a sigmoid function is that softmax function is the one that is suitable for multiple class classification. It is a modification from the sigmoid function to capture multi-class classification. Okay? So what we just discussed earlier is that neural network architecture and activation functions are two very important concepts in neural network. While the network architecture defines how this structure will be, this activation is responsible for introducing non-linearity to the network. And these activation functions has to be added or exist in every single neurons. All good? I think it will be clearer when we try to train a network in next week practical. You will come to see that we will be using some activation functions. How do we define that in every single neuron? Okay. So then what's next? So in the process of training a machine learning algorithm, we often talk about this loss function. Loss function is, what is loss function? Loss functions is a way to calculate the error which a model is seeing, okay? Error. So they quantify how well a network prediction matches to the actual outcome. So the process of training any machine learning algorithm is a loss optimization task. Loss optimization means what we are trying to do is adjusting the weights in order to minimize the loss. Minimize the loss means minimize the error. Okay, so we want to go over 3 types of loss function that we commonly use when we train a model. So the first one that we want to cover is binary cross entropy loss function, and the formula of binary cross entropy loss function is given as this. So over here it is very easy to understand. We can just understand it easily as the y with the hat is our predicted output, and the y that without the hat is our predicted output. So now we are taking the sum of the difference between our predicted output and our actual output to take it as our loss function. So the difference between binary cross entropy loss function and categorical cross entropy function is the way of how we treat this, how we compare the difference between our actual and the predicted values. So over here, if we have a multi-class classification problem, categorical cross entropy quantify an extra dimension of these differences, which is by the number of classes. Okay? And if we were to use our neural network for a regression task, then the loss function which we will be using to quantify the loss in the process of training process will be exactly the same as the loss function we use to train multiple linear regression. That is mean squared error loss. Okay? So the point here is that the loss function is a way for us to quantify the error. And this error should guide our learning process towards minimizing the error or the loss. So now what we just covered is the architecture, the backpropagation mechanism, and how do we quantify the loss. So now there is one last concept that we have to cover to fully understand how this neural network learns from our data. So the final concept that we want to walk over is the gradient descent. So what is gradient descent? So we know that this neural network is going to learn from our data forward and backward. And in this process, what we are trying to do here is to adjust the weights, the W. So we will be applying some mathematical function for us to adjust the W according to a certain rate. So then how this network knows how much to adjust every time we have a backpropagation, right? And that is the concept of gradient descent. So this gradient descent is an optimization algorithm. It is again very complex mathematical function that helps us to decide how much we should adjust the weights every time we see a certain level of error. Okay, so the main idea of this gradient descent is that we can imagine if, let's say, we have a model or neural network with 2 input. So we have theta 0 and theta 1. Okay. So what we are trying to do here is every time we will update this value. We will update the weights for this parameter and the weights for this parameter, and we'll have a pair. Our loss function is usually quantified as J. So now we have these two parameters and the quantified loss function. What we are trying to do here is every time we randomly initialize a certain set of weights, the error will be computed. And we assume that every time we randomly initialize this weight, it is going to arrive at a high point, high error. Okay? So now what this process is trying to figure out is every time it backpropagates and updates the weights, it wants to try to achieve a state which has a lower error compared to the previous set of weights. Okay? So imagine the landscape. So where the loss function represents the height of the terrain, so this gradient descent aims to find the valley or the minimum in this landscape. So this is just an illustration, yeah. So it takes a lot to plot this entire graph. So now our randomly initialized weights will result in a high point always. So it always starts with the initial position and iteratively takes steps to arrive at the steepest descent, the negative descent. And this minimum point is the point that we want to get to for every single steps of weights adjustment. With every single step, the loss function ideally decrease, leading to network closer to optimal solution. Okay, so now this is the idea of gradient descent. So what it takes here is, what we want to take note here is, how fast should we go? Say, for example, if we were to train a machine learning algorithm, we can do a stepwise approach where let's just turn this chart into a 2D dimension so that it's easier to explain. So now, the underlying principle of how much should we update the weights is the learning rate. So this learning rate is a very important parameter whereby if we are setting a too large learning weight, we will result in this output. So our network at the back end, it will be training from one point to another. And at the end of the day, we might not be able to arrive at the point that we are trying to arrive at, which is the minimum, the point with minimum loss. Okay? But if it is too slow, it takes very long to converge. So that means some of you who are training image classification task, this is what you will see. If your neural network is taking too long, that's probably because we are taking a too small learning rate. So it is learning too slow from our data set, which means that it will never arrive at its lowest point towards the end of our epoch. Yeah? So it is very important for us to optimize the learning rate. So what is a just right learning rate is then the rate that allows this neural network to learn or to discern at a stepwise approach. So then the concept here is that we can take a very constant learning rate where we will standardize its learning rate. But there are also some other idea which is able to capture the momentum of the descent. Say, for example, if let's say this neural network update this weight at a certain rate, say for example, at a certain rate, and this network finds that, okay, the error is reducing, and therefore it is being able to capture this momentum and pass on the momentum to the next round of training. It will adjust the weights a little bit with a larger gap, with a larger leap, so far and so forth. And when it reaches a plateau, it will then adjust the rate of updating the weights towards a smaller gap. So all of this gradient descent way of way of learning from our data, this gradient descent, they are called the gradient descent algorithm. So we have stochastic gradient descent, mini batch, momentum, adder grad, and also Adam. So these gradient descent algorithms are fully optimized for a certain ways of capturing the learning rate. And therefore, it is worth looking into in the case where we are training a complex neural network, okay? Because this gradient descent is going to be a factor that affects how accurate our neural network is. And that is the concept of gradient descent. So in gradient descent, what matters to us at this level will be, this gradient descent is a way for us to figure out how to optimize the loss, how to train our model. And what is important, the principle behind is the learning rate. Okay? Question? No question? Okay, so as a summary of today's lecture, what we just covered is how this artificial neural network learns. So now we started off by talking about the basic unit of neural network, which is a perceptron, and a very important way of how this backpropagation works. Then we go and we talk about this activation function, which is one of the most important aspects which introduce non-linearity to our neural network. And finally, we talk about this gradient descent, which allows, which defines how fast or how slow we should train our neural network. And that is for today. I will see you next week. So, have anyone have the answer on the previous question that I asked? What is the difference between hyperparameter tuning and grid search? And is it normal for hyperparameter tuning to achieve lower accuracy? Hyperparameter tuning is a process where we want to fine-tune the hyperparameter of a particular algorithm. These hyperparameters are usually not visible at the front end of our model. So say, for example, hyperparameter for our linear regression will not be the coefficients. Instead, these hyperparameters will be the regularized